Hello everyone, this is Sudeep here. Welcome to my channel Math Scout. In my previous video of COV, I discussed about finding extremum using Euler equation. Now what is the Euler equation? Euler equation is del f by del y minus ddx of del f by del y dash equal to 0, where f is our functional. And how it is defined? It is defined by I of yx equal to integration x1 to x2 f of x comma y dash dx, right? Today I will discuss about isoperimetric problem. Now what is isoperimetric problem? In this problem, a functional is given and the corresponding boundary conditions are also given. Another extra constraints is given. See, suppose I of yx equal to integration x1 to x2 f of x comma y dash dx. It is our functional and the boundary conditions are given. There y at x1 is y1 and y at x2 is y2, and a constraints is given that is integration x1 to x2 g of x comma y dash dx equal to some constant k. This type of problem is known as isoperimetric problem. Now, how to deal with this type of problem? We have to make another functional, say capital F. How? Taking this previous functional and the constraints like that, f plus lambda into g. Here lambda is Lagrangian multiplier. Now we have to use Euler equation del f by del y minus ddx of del f by del y dash equal to 0. Here this f is our new functional. Now see one problem for better understanding. The extremal iy equal to integration 0 to 1 y dash square x dx subject to y0 is 0 and y1 equal to 1 under the constraints integration 0 to 1 yx dx equal to 0 is, these are the options. Now see, this is functional, these are the boundary conditions, and this is our constraints. Now what we have to do? We have to make another functional, say capital F equal to small f plus lambda small g. Now what is small f? This is our small f. So y dash square plus lambda into g. G is given as y. So this is our new functional. Now you have to use Euler equation. What is our Euler equation? Euler equation is del f by del y minus ddx of del f by del y dash equal to 0. Now put capital F here and here. What we will get? We will get lambda minus ddx of 2y dash equal to 0. Now ddx Now ddx of 2y dash means 2y double dash equal to 0, right? That is 2y double dash equal to lambda. So y double dash equal to lambda by 2. Okay. Integrating this, will get y dash equal to lambda x by 2 plus c1. Here c1 is arbitrary constant. Again integrating, we will get y equal to lambda x square by 4 plus c1x plus c2. Here c2 is another arbitrary constant. We have to find the value of lambda, c1 and c2 using the boundary conditions and constraints. Now put the boundary conditions here, that is y0 equal to 0 and y1 equal to 1. See, y0 equal to 0, that is if we put x equal to 0 here and here, we will get y equal to 0. So this is 0, 0, 0. So c2 will be 0, right? And y1 equal to 1, that is if we put x equal to 1 here, we will get y equal to 1, that is 1 equal to lambda by 4 plus c1, and c2 is 0 here, right? So we get the value of c1, which is 1 minus lambda by 4. Now we have to use the constraints, that is integration 0 to 1 y dx equal to 0. What is the value of y? Y is lambda x square by 4 plus c1x plus c2, and we get c2 is 0 and c1 equal to 1 minus lambda by 4. So integration 0 to 1 lambda x square by 4 plus 1 minus lambda by 4 into x dx equal to 0, right? Now what is the integration of lambda x square by 4? It is lambda x cube by 12 plus 1 minus lambda by 4 into x square by 2, and the lower and upper limit are 0 and 1 respectively, right? If we put upper limit, then it will be 1 and 1, and if we put the lower limit 0, so these will be 0. That is lambda by 12 plus 1 minus lambda by 4 into half equal to 0, right? Now after calculating, we will get the value of lambda, that is lambda equal to 12. Now put this value here to get the value of c1, and you can see the value of c1 is 1 minus 12 by 4, that is 1 minus 3, so minus 2. Now put c1, lambda and c2 here, we will get the value of y, that is y equal to, if we put lambda equal to 12, so 12 by 4 is 3x square minus 2x plus 0, that is 3x square minus 2x. So our correct option is option A, 3x square minus 2x, right? Now see another example of isoperimetric problem. The extremal of the isoperimetric problem Iyx equal to integration 1 to 4 y dash square dx. These are the boundary conditions and this is our constraint. Okay. Now we have to make a functional using this one and this one. Okay. So capital F is y dash square plus lambda into y. This is our new functional. Now use Euler equation. What is Euler equation? Del f by del y minus d dx of del f by del y dash equal to 0. Okay. Substitute this value here and here. We will get lambda minus d dx of del f by del y dash, that is ddx of 2y dash equal to 0, right? And ddx of 2y dash is 2y double dash, so lambda minus 2y double dash equal to 0, that is y double dash equal to lambda by 2. Fine. Now to get the value of y, we have to use integration. So integrating this with respect to x, we'll get y dash is yx by 2 plus c1. Again integrating, we'll get y equal to lambda x square by 4 plus c1x plus c2. Now use these boundary conditions, y1 equal to 3 and y4 equal to 24. So y1 is 3, that is if we put x equal to 1 here and here, we will get the value of y which is 3, that is 3 equal to lambda by 4 plus c1 plus c2. And if we put these boundary conditions, that is at x equal to 4, the value of y is 24. So 24 equal to lambda into 4 square by 4 plus c1 into 4 plus c2, that is 24 equal to 4 lambda plus 4 c1 plus c2, right? Now if you look very carefully the options here, we will find the options are parabola, circle, straight line and hyperbola. And here y is this, right? No need to check the boundary conditions because we know the equation of circle, this should be x square plus y square into some constant type. So this never be a circle, okay? Option C, straight line. This never be a straight line because lambda is non-zero for isoperimetrical problem. That is why this is never be a straight line. And in case of hyperbola, the degree of y should be 2 and x also, but here the degree of y is 1. So this never be a hyperbola. So the only option parabola is our correct answer. No need to check the boundary conditions here. Remember, in exam this type of question may arise, so be careful. Now one more type of problem is very important regarding CSIR net for COV, that is functional having more than one variables. Here the functional is I of y1x, comma y2x, comma y3x, comma dot dot dot. Okay, here you can see there are more than one variables and it is defined as integration x1 to x2 f of x comma y1 comma y2 comma dot 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 and their first order derivative, that is y1 dash y2 dash dot 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 of dx, and the corresponding boundary conditions are given for each variable. Okay, how to deal with this type of problem? We have to use Euler equation for each variable. Okay, that is we have to use this equation del f by del yi minus ddx of del f by del y I dash equal to 0. And what is I? I is 1, 2, 3, 4. That is we have to use Euler equation for each variables. Okay. Now see an example for this type of problem. Find the extremal of functional I of yx and zx. You can see there are two variables. Now to solve this, we have to use Euler equation for both y and z separately. So what is our Euler equation? Del f by del y minus d dx of del f by del y dash equal to 0, and del f by del z minus d dx of del f by del z dash equal to 0. Okay, what is f? F is here y dash square plus z dash square. Here y1 means y dash and z1 means z dash. Okay, that is the first order derivative of y and z respectively. So this will be 0 minus d dx of 2y equal to 0, and here also 0 minus d dx of 2z equal to 0. That is, if we put this here and here, we'll get this is 0 because no term of y is here, minus d dx of 2y dash because this is y dash square, and partial derivative with respect to y dash is 2y dash, so this is 2y dash. Similarly this 2z dash. Okay, now see d dx of 2y dash equal to 0, that means 2y dash equal to some constant, say c. Okay, similarly 2z dash equal to some constant, say d. Now to find the value of y, we have to use integration. So integrating, we get 2y equal to cx plus d, that is y equal to c by 2x plus d by 2. This is our arbitrary constant, so let this another constant ax plus b, that is y equal to ax plus b. And if we perform the same technique, we will get z equal to, say, px plus q. Fine. Now we have to use our boundary conditions for y and also the boundary conditions for z. So using y0 equal to 0, we will get, if we put x equal to 0 here, we will get y equal to 0, so b equal to 0. Again, if we put y1 equal to 1, we will get 1 equal to a into 1 plus 0, that is a equal to 1. Therefore y equal to x. And if we put z0 equal to 0 here, we will get q equal to 0, and if we put z1 equal to 2, we will get p equal to 2, right? Therefore z equal to 2x, and these two are extremum value of y and z respectively. In my today's video, this is my last concept. What is that? This is functional having higher order derivative. Here the functional I of yx is given as integration x1 to x2 f of x comma y dash comma y double dash comma y triple dash comma dot 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 so on of dx, and boundary conditions for each derivative will be given. Okay, how to solve this type of problem? We have to use Euler equation, but we have to modify our Euler equation. For this case, Euler equation will be f of y, that is del f by del y, minus d dx of f y dash, that is del f by del y dash. Now see, this is our previous one, but here higher order derivative involved. So d2 dx2 of del f by del y double dash minus d3 dx3 del f by del y triple dash plus dot dot dot. Understand? So what will be the last term? Last term will be minus 1 whole to the power of n dn, sorry, there n minus 1, because see, this is our first term, so no derivative. This is our second term, first order derivative. So this is our nth term, so n minus 1 th power derivative del f by del y nth derivative, this will be 0. This is our modified Euler equation. Now see an example for this type of problem for better understanding. Find extremal of the functional I of yx equal to half of integration 0 to 1 y double dash square dx, y0 is 0, y1 equal to half, y dash 0 is 0 and y dash 1 is 1. We have to use Euler equation, that is del f del y minus ddx of del f del y dash plus d2 dx2 del f by del y double dash equal to 0, because see, in functional the highest order is 2, so we go up to second order derivative. Okay, now use this here, here and here. This two term will be automatically 0 because no term of y and y dash, so only remaining part is this, that is d2 dx2 of 2y double dash equal to 0. Okay, now the second order derivative of 2y double dash is 2y, the fourth order derivative equal to 0. Okay, that is y fourth will be 0. Fine. Now to find the value of y, we have to integrate this up to 4 times. So y triple dash is some constant, say c1, where c1 is arbitrary constant. Again integrating, we'll get y double dash is c1x plus c2. Now c2 is our new arbitrary constant. Y dash equal to c1 x square by 2 plus c2x plus c3. Okay, again if we integrate, we'll get y equal to c1 x cube by 6 plus c2 x square by 2 plus c3x plus c4. Okay, now we will use the boundary conditions, that is y0 equal to 0, y1 equal to half, y dash 0 is 0 and y dash 1 is 1. Y dash 0 equal to 0 gives this term and this term is 0, so c3 will be 0, that is this term will be 0. Okay, and we also given that y0 is 0, that is if we put x equal to 0 here, 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 this time will be 0, so c4 is also 0, right? Only remains y equal to c1 x cube by 6 plus c2 x square by 2 and y dash equal to c1 x square by 2 plus c2 x. Now also given y dash 1 is 1 and y1 is half, so if we put x equal to 1 here and here, we'll get this is 1, so 1 is c1 by 2 plus c2, and if we put x equal to 1 here and here, we'll get y is half, so half equal to c1 by 6 plus c2 by 2. Now if we calculate these two equations, we will get the value of C1 and C2. Calculating, we will get C1 is 0 and C2 is 1. Therefore, we will get the value of C1 is 0, C3 is 0 and C4 is 0 and C2 is 1. So, if we put here, we will get y is x square by 2. So, this is our extremum.